on time. We can wait for other attendees resistance.
Okay, good. Yeah, I think by 5 we will launch it.
Yeah, sure. Today, more than 600 people have registered for today's webinar.
That's good.
Yes, we expect more than like at least around 300 maybe will be attended.
Okay, that's good.
Yeah.
Hello, everyone, and welcome to today's webinar from MIDAS Academy. And the webinar topic is about load rating of steel used through bridge. As an overall for today's presentation, I will start with a brief introduction about myself and about the company I'm working for, which is SMEC, and then we will head up toward the core of the subject. My name is Abdullah Zaid. I was born and raised in Yemen, and then I moved to Malaysia to do my undergrad and postgrad studies. Then before 3 years, I moved to Australia. I have more than 11 years of experience, mainly in bridges and general structure. And I have most of my experience are really in bridges, and I have experience in highway, railway, and cycleway bridges. I've been with SMEC for about 3 years. I've started with SMEC Malaysia for a couple of months, then I've moved to Sydney. This is just a picture about my country, Yemen, and this is the capital city, Sana'a. SMEC stands for Snowy Mountain Engineering Corporation. It's attributed mainly to Snowy Mountain Hydroelectric Scheme project, which is one of the engineering wonders. In 2016, Surbana Jurong acquired 100% of SMEC Group, and SMEC together with Surbana Jurong are highly ranked among the international design firm and global design firms. A list from the engineering news record. Few of the latest awards and accreditation received by SMEC are listed, and what we embrace in SMEC is our culture. I mean, since I joined SMEC, I felt really welcomed by everyone. And one of the recent projects we have completed is Sydney Metro Northwest on the picture here. And this project has won various awards. The presentation scope will start with an overall introduction about load rating and why we need the load rating for bridges. And then I will go to the case study of a bridge we have done in SMEC. I will explain the bridge details and how is the bridge current condition and how did we do the modeling, and a brief overview of the results, and we will finalize our presentation. The objective of today's presentation mainly, and what everyone expects to gain from today's webinar, is understanding of the levels of bridge investigations, and then how we undertake the load rating and the fatigue assessment. Why we need to undertake or to do load rating? Generally, we have aging structures. Some of the structures in Australia and around the globe have been built last century or the century before. So it has been like more than 100 years. And with the development we are going through, there are a lot of demand for increased loading as well. So like given the Sydney Harbour Bridge was built in 1932, which now it's 88 years, definitely the trucks that used to exist in 88 are different than the one we see in the streets today. And there are a few occasions around the globe where bridge collapse has happened due to overloading. And in this picture, you can see a bridge collapse in India. And it's also important from the asset management point of view to make the asset management more efficient. The difficulties we experience with old bridges is sometimes we don't have a date for a bridge. When was this bridge built or designed? Because an early estimation of how good is the bridge is when was it built and what codes the bridge were built to. So that will give us a first estimate of what sort of loading can go through that bridge. And also the availability of the drawings. Some bridges we don't have even, we don't have drawings for them. I'm quite interested on the old hand sketches and the simplicity of the drawings for, earlier engineers, which probably will have only a few drawings for a bridge. But the problem sometimes we can't have those drawings. And also from the fatigue perspective, we need the loading history for the bridge. And we will get into details later. Bridge assessment standards. We have in every country or in different continents and countries, they have different codes. But in Australia, we have the overarching code AS5100, which used nationwide. And we have different parts, and part 7 is especially for bridge assessment. And then we have a state and client requirements as well. So each state in Australia has its own guidelines on how we undertake the bridge assessment. In New South Wales, that's where Sydney is, we have, for example, the ASA or the Asset Standard Authority, that's which gives us a guidelines of how we undertake the bridge assessment. And other states like Victoria and Queensland and other states as well, they have different guidelines and manuals. In general, there are overarching steps for the bridge assessment, which is also given on the AS5100, part 7. But in general, we have levels of assessment, which is basically level 1, 2, and 3. And level 1 is mainly to check the general serviceability of the structure and identify any emerging problems. Then we have level 2, which is a bit more comprehensive visual inspection. And in level 2, we will do a specific rate, to rate the condition of each component of the bridge. Then we have level 3, which is a detailed engineering investigation. This includes field investigation and also a structural analysis. That's where the load ratings come. The fatigue assessment is also in level 3, and fatigue is an interest topic, and especially for steel bridges. And then we have the rehabilitation and strengthening. So from the flow chart on the right-hand side, we can see the steps that we generally follow for the bridge assessment. We start with data collection. That's to look whether we have drawings or previous condition assessment of the bridge. And that's also for the assets authority, for them to identify the number of assets and the location of the assets as well. Then we have the bridge condition, which tell us whether the bridge is in a good or poor condition. Then we have the field geometry. That's especially if it's an old bridge, sometimes we don't have a drawing, as I mentioned before, or sometimes there have been like a lot of modification to the bridge. So we need to take that into consideration when we do the bridge assessment. Then we move to the capacity assessment. That's basically take the individual component of the bridge and calculate how much are their capacity. After that, with modeling and analysis, we undertake the analysis to find out the load effects and the load factors. Then we have the fatigue assessment. And after that, after we finish all that, the bridge assessment and load rating will be done via an equation given in the code. If the bridge has an adequate capacity, then when we finalize the assessment, but if it is not, then we have to undertake either like a higher tier assessment, if that's an advantageous, like nonlinear analysis or a specific and site investigation and load testing. And then if that's fine and the capacity could be validated, then it's fine. But if it is not, then we have to impose sometimes some restrictions on the bridges. Why we need to do this bridge assessment? It's effective for asset management perspective. So we reduce overstressing of the structures. So we maintain their reliability and the life cycle of them. And it's ultimately for it's more safer and for this, the safety of the users. And it helps also to reduce the cost of maintenance. Load rating. So when we undertake the load rating, we have different steps as well. So we start with the as new load rating. Basically, the as new load rating is the design load of the bridge with regards to the as built drawing. So this is assuming the bridge just built, and based on the drawing, what is the capacity of this bridge. Then we have to undertake the structure mapping and condition assessment. This is basically to identify any deficiency on the existing bridge, like suction losses or cracks and spalling of concrete. And if there is also from the structure mapping perspective, if there is any new members or strengthening of the bridge, or maybe some additional structure to the bridge itself. So that's we have to undertake that in our assessment as well. Then we have, after the as new load rating, we have the as is load rating. So this, when we undertake the as is load rating, it's basically to illustrate how much capacity has the bridge lost during its lifetime. So that could be due to the corrosion or any other external impacts. And then after that, we undertake the fatigue assessment. Basically, the fatigue assessment, the bridge could sustain the load from the ultimate limit state point of view, but the fatigue assessment has a limited life for the bridge components or members, and we need to check based on the loading history how much of that fatigue life has passed and what is the residual remaining life of the bridge. The fatigue assessment or the fatigue analysis has gained a bit of interest, and it's mainly because there have been few bridge failures, especially steel bridges, and the reason is attributed to the fatigue. That's why we have heard about bridge, or we have experienced a bridge failure for bridges that lived for 50 and 80 years, and they collapse at the end. So there are different reasons for that, and one of them is the fatigue loading. So to give you an overview of the fatigue, basically when we design a bridge to ultimate limit state, we will just see how much is the ultimate strength of the section, and we can load that section to its ultimate capacity. Nothing will happen. But if that stress or that load has been repeated 100,000 times or millions times, then as we see, the fatigue capacity will reduce with the increase of the load cycles. So for instance, if we have a stress of sigma A1 that in a structure or in a bridge, so for that stress, we can only load the bridge in one cycle's time. So if this N1 is a million cycles, so we can have that stress to run a million times. But if we expect the bridge to have more than 1 million cycle, then we have to reduce the stress by increasing the section. And this is very important. This analysis is very important for fatigue sensitive structures like the sign structure or the highway sign structures, and also for the bridges. And we can see that the more cycles we have, the lower stress need to be designed for. And from this bridge from this graph from the literature, it has a cutoff limit, but based on the recent code AS5100 2017, this cutoff limit seems to be disappearing. So previously we believe that if the stress is low, we can have unlimited number of cycles, but from the new code, that still accounts. Even the low stresses still accounts. Even it's an algorithmic like relationship, but it still accounts and it still contribute to the damage. So we will get into the bridge details. So basically, this U-through bridge is a rail bridge, and we call it in Australia as steel under bridge. Basically, it's been differentiated between the underbridge and overbridge. The underbridge is basically any bridge that carries rail, and the overbridge is for bridges that carries roads. The bridge was built in 1914, which gave 106 years. And the span is heavily skewed in 27 degrees, as we can see from the plan. That's where the apartment is. And this type of structure is U-through girder. It has, the span is 25 meter and the width is 8.2, and the substructure is masonry abutment. Basically, the U-through girder or the U-through bridges consists of main girders or the through girders, and then we have a cross girder, which I will show you the picture in the following slide. So this is the bridge at site. There are 3 bridges with the same dimensions. The main girder, it has 2 main girders, as we can see, and the U-through girder advantage is to minimize the structural depth, because most of the structural depth, as we can see from the photo on the left, is above the rail level. So it maximizes the clearance underneath the bridge. The main girder is 2.5 meter deep. It varies because we have like more plates at the center of the bridge or the center of the span, but it's about 2.5 meter. The cross girder depth is 0.85 meter, and the stringers is between 355 to 500 millimeter. So this mainly the internal stringers, and the end stringers are deeper because they are longer, as we seen here. So those stringers are longer. We have the transoms, as we can see from this picture. They are a timber, and we have the cross bracings, which are like equal angle structure, and then we have connections. Basically, that's what connect or riveting the cross girder to the main girder and the stringers to the cross girder. So as I have explained, I mean, what is the parts that making the bridge, or what are the components of the bridge itself. But there have been like questions of what we need to model and whether we need to model everything. So from engineering judgment, the engineer should have the ability to judge and um, model the things that affect the structure behavior. So it's not the interest of modeling everything, because with the advanced softwares we have like MIDAS, we can model everything on the bridge, like cross bracing, the connections, and the rivets and everything. So it's like whether we need to go to that depth or not. So I've illustrated that with two types of modeling. We have the grillage model and FEM model. The grillage is simple line models, but the FEM models is more into like plates and 3-dimension uh, modeling of each component, or such as the webs and the flanges with the stiffeners and the connection. This model is done by one of my colleagues in SMEC as well. So what I have modeled mainly, or what's been modeled in the grillage, is the main girders, the cross girders, the stringers, and the transoms, just to transfer the load. And then cross bracings, because they are mainly for stability, we haven't modeled them, and also the connection for the basic model were not modeled. The bridge condition. So we have typical issues with steel bridges, like corrosion. As we can see, this is like a corrosion in the top flange of the stringers, and this is also the bottom flange of the stringers around the abutment. And also we have seen some missing bolts as well. Then for the bridge condition, we have undertaken a structural mapping. Basically, the structural mapping scope is to identify any like old members being replaced, or any new members that has been used to strengthen the bridge. Also, any strengthened elements, like as we can see in this member, this is a stringer with a welded additional plate on the web. And also a change for the section capacity, where we have like losses on the top flange, bottom flange, or the web. We have to identify those and estimate how much is the capacity after the section losses. So it's also important for us, after doing the condition assessment, to think whether the changes happens to the bridge. Do we need really to remodel the bridge and use the new sections or the new members or not? So this has to happen in case-to-case basis. If the element will change the stiffness of the bridge, we would need to rerun the analysis. But if it is only contributing to the section capacity, we might not need to remodel and reanalyze the model or the bridge. That's what happened on our bridge. So from this like structure mapping, we can see some of the stringers has been replaced, and also some of the cross bracings as well. And we have also, as I've shown in this picture, we have additional plates to the webs. So coming to the bridge modeling. So the type of analysis we use is basically a linear modeling for longitudinal analysis. What is the purpose of that analysis is to obtain the forces for different load types, and mainly for moving loads. And we have then to calculate the fatigue stresses via the time history analysis, which is a bit interesting part of this bridge scope and this presentation as well. And then after that, we have to calculate the section capacity of the structure members, so then we can do the load rating. So how we model the bridge, basically, we have created sections for all the components, which are like the main girder, the cross girder, and we have the stringers. So as we can see in this like screenshot from the MIDAS model, we have three main girder sections because we have different depth of, additional plates at the center of the bridge, as I mentioned before. And it's illustrated here also on the cross girder as well. So we can see it's a riveted built up section. We have a section where it's only like single flange, top flange and bottom flange toward the end. Then it goes to 2 blades riveted. Then it goes to 3 blades. So that's why we have 3 sections for the same cross girder. We can see also the stringer and how it's connected to the cross girder. And also we can see the connection between the main girder and the cross girder, which are via this riveted connection. So how we define the section? The section has been defined with the coordinates, defined by coordinates, and that's where we could input all the coordinates for the top flange, the web, and the bottom flange, calculating the effective area, which it's very useful. There are different ways to model the bridge and the sections, which is an advantage with MIDAS. You can model things, whether it's in a CAD, then transfer it, or you can build up your model, your sections and model on the MIDAS itself. So the boundary condition. So we have bearings at the end, and also we have the connection, which needs to be modeled also. And that's where we define the support reaction based on the bearing from the drawings and also at the site inspection. And then we have the beam end releases, because as we can see in the connection, it's not really a fixed connection with top flanges connected, fully connected to the web or to the main girder. So there is some releases of the bending moment. It's also at the stringers as well. It's being considered as a pin connection while it's only through the web. The web is connected to the member. If the connection has a top flange connection as well, it will transfer the moment as well. So the boundary condition, basically we have a roller bearings at one side and fixed bearing at the other side. And we have a sliding bearing for the stringers. So we can see that's the main girder, and we have 2 supports. One will be fixed and the other roller. And that's one main girder, and this is the second. Yeah. Let's see. Okay, so this is the first main girder, and that is the second one. And then we have, these are just the stringers connected to the cross girder, and we can see also the green circles around this area, which is the moment release, or the end releases that apply to the moment, or to the members, sorry. Okay, we need to get rid of, I'll just leave them. So what type of loadings we have used? So we have dead load, superimposed dead load, and we have the live loads, which is the moving loads we applied on the bridge, and then we have the wind load. So for the live load, we have different type of moving loads, which is the 300 LA, is basically the train loads or the heaviest train loads in the code. Then we have the Warata electric, is basically the passenger trains, and we have some freight trains and other loads identified by the client. For the fatigue assessment, we would need to undertake a specific loading arrangement. So we have to apply not idealized maximum loadings of the bridge, but rather the actual loading that been traveling on the bridge itself. So this has a specific load arrangement, and we will come to it in a second. So the types of live load, as we can see from the code, we have the 300 LA rail traffic, which is defined here, and we have the Warata electric, which is also given, like this is just a single car, and this in this picture I'm showing the trains that we use in Sydney. They are double-story trains with what we call a Warata electric. And from the historic, for the time or for the fatigue assessment, we needed the historical data. So from the real resource center or from the historical data of the trains that traveled that bridge, we managed to identify 9 types of trains, and these trains has different arrangement. This arrangement is crucial for identifying the stress ranges and the number of cycles for the bridge. This is very important when we undertake the fatigue assessment. And I will cover the fatigue assessment in a minute. So we have 9 types of loading or specific loading that has been traveling that bridge, and apart from the load rating for standard rail loading. The time history analysis, basically on MIDAS, when we run the moving load, we will get, the MIDAS will run an influence line method, which will give us the maximum forces. This will give us the maximum moments, shear force, torsion for each member. And from the live load tracer, we can see which load has caused that maximum loading. But the issue with the fatigue assessment, we are not looking at one single result or the maximum loading. Rather, we are looking at the fluctuation of stresses when a moving load is applied. This is where it's become very important for us to undertake the time history analysis. MIDAS provide that. It was designed originally or mainly for a seismic loading, but it's been useful also for tracking the historical loading from a moving load as well. There is a specific training of how we use the time history analysis for moving load to identify the stress fluctuation on a single element as a moving load bus. And this training will be on next week, 11th of June, and it's available on MIDAS Academy, and this is a link for registration as well. Coming back to this graph, just a bit of stress history for end cross girder. So as we can see, there is 3 graphs and for 3 types of trains. And what we need to look at for the fatigue assessment, we would need a stress cycle, and then we need also this is we consider like the range of the stress. For example, in this orange colored, the range is between 0 and 45. It's about 45 MBA. That's the stress range, and we need to calculate how many stresses, how many cycles, like 1, 2, 3, 4, 5, 6. There is 6 cycles of around 45 MBA. Then with these cycles, number of cycles and stress range, we can then calculate how much is the fatigue damage, what is the actual fatigue damage to the structural element. So then basically from the results of the load rating, we can extract, as I mentioned, the maximum forces for bending moment and shear force. This is the global model with the bending moment diagram, and it's as a result from the 300 LA loading. And it's quite useful in MIDAS how we can extract the results, whether it's like in a table format or a graphical format as well. This is a graphical format for the main girder with uh, uh, the loads shown on this legend, and also for the internal cross girder we can see the bending moment diagram as well. For the shear force is similar. We have, this is the shear force for the main girder, and also the cross girder is shown in this diagram. This is the stresses from the historical loads, the historical load stress from the time history analysis. This is what we will extract for the fatigue assessment. We will have the loadings or the stresses. This is for the shear force, and that's for the bending stress at a specific location on the bridge. So this will help us to calculate this stress cycle ranges and count, and we will do the count. Basically, the code gives us two methods to do the count of the stresses. Basically, it's based on either like the reservoir method or the rain flow method. And this is a different topic which needs a different probably seminar or webinar to go through how we calculate that. There are many references available online how we do the cycle counts for a like a moving load. Now we come to the load rating factor. So we have calculated now, when we modeled, we know what is the design effects, and we have checked the member capacities. We calculated the member capacities. Then we will be able to use this formula from the AS5100 to do the load rating, or as they call it, rating factor. The rating factor will give us, if we are checking like a 20-ton vehicle, we'll be able to check if the rating factor, if it is above 1, then this bridge can accommodate the 20-ton vehicle. But if it is the rating factor is below 1, then we have to limit the weight on the bridge. So from the section capacity we have done, in this table I'm giving just a summary of the bridge components, and then we can see the results for the as new capacity and as is capacity. So as I've explained earlier, we have the as new capacity assuming the bridge just built, and this is the ultimate capacity that the bridge can take, but the as is considering all the corrosion happens and the impact on the structure. So we can see most of the elements has a reduced capacity from the corrosion. Rating factors. So this is a summary for the rating factor for one load case, which is the Warata Electric, 2 tracks loaded. So we can, that's how the code define it, or how the local authority define it, how they want the results to be presented. We have to show the bridge component, which is different, like the through girder, cross girders, and the stringers. Then what design actions we are checking. This is the dynamic load allowance, and then we have the as new rating factor, and then the as is rating factor. So as long as all those factors above 1 is fine, but as we can see in this, the end stringer has a capacity or loading rating factor below 1. So this is marginally below 1, which needs further investigation as well. And here are the results for the fatigue residual life. Basically, what we have done specifically for this bridge, the client asked us to undertake the fatigue assessment based on two codes, the 2017, which is the recent copy of the AS5100, and also the 2004 copy of the AS5100. So we have undertaken those two just for understanding how the changes in the code affects the results. So from the analysis we have undertaken, we found out the end cross girder and the intermediate cross girder has exceeded their fatigue life, but considering the 2017 code, and it's approximately 3.6 years of loading will bring it to the full fatigue damage, or the full fatigue damage for the end cross girder for 2004 issue of the code. We don't have to do that for every bridge, but because when we got this project, we were transferring from 2004 to 2017, and it was an interest for the client to understand how the changing the code will change the results. So as a conclusion for the bridge analysis itself, so we have found more that the bridge required more detailed investigation because there were some deficiencies, not only in the Warata electric, not only in this load case, other load cases has resulted in some deficiencies, and that's why we needed to undertake a more detailed assessment, and we went for nonlinear assessment as well, nonlinear analysis of that bridge. And also for the fatigue, the cross girders are critical for fatigue analysis as well. So they need to have more investigation, which is a fracture mechanic investigation for the cross girders as well. So overall, to summarize our webinar, we started the bridge analysis, or the bridge assessment with data collection, where we got all the drawings. Then we have done the bridge condition assessment. After that, we verified everything from the field geometry, and with the condition assessment and the structure mapping. After that, we went for the capacity assessment of the bridge with load rating and fatigue. And what we found from the results using the rating factor, that there is no adequate capacity, so we needed to do a higher tier assessment, which went for nonlinear analysis. And now, after that, when we finalize this analysis, we will go to the final conclusion, whether we will restrict the loading or we will strengthen the elements.